Hi, I'm Zara, and this is FlashForward, a multimodal neural learning pipeline that transforms raw lecture material like audio or PDF notes into structured study materials, powered by Whisper, Sentence-BERT, and Phi3. Here's what I will be covering today. I'll start with the problem, walk through the three neural network models, explain the end-to-end pipeline, show application features, and finish with references. After the slides, I will do a live demo of the Gradio app. The core problem is this: students sit through lectures and are left with raw audio and unstructured notes. Traditional approaches completely fail here. Old speech-to-text systems break down on noisy audio or domain-specific jargon. TF-IDF keyword matching has no semantic understanding. It cannot tell you if a student actually understands a concept, just whether they use the right words. And critically, standard tools lose all temporal context when converting audio to text. You have no idea where in the lecture something was said. The neural approach solves all of this. An encoder-decoder transformer extracts text and preserves their exact timestamps. A Siamese-BERT network projects sentences into vector space so we can mathematically measure semantic similarity. And a large language model synthesizes everything into flashcards, MCQs, and personalized feedback. So FlashForward runs on three pre-trained neural networks simultaneously. First, OpenAI Whisper, which is a sequence-to-sequence encoder-decoder transformer. It takes the raw audio waveform, converts it to a log-mill spectrogram tensor, and outputs text tokens along with their acoustic timestamps. It was pre-trained by OpenAI on 680,000 hours of multilingual supervised audio. No fine-tuning was needed here. Second, Sentence-BERT, specifically the all-mini-LM model, which is a Siamese neural network with a 6-layer mini-LM transformer at its core. It maps any sentence into a 384-dimensional dense vector space, which allows us to mathematically compare meaning. It was pre-trained on over 1 billion sentence pairs. Again, no fine-tuning required. Third, Microsoft Phi3 Mini. This is a 3.8 billion parameter decoder only transformer, the generative brain of the application. Because of VRAM constraints on the T4 GPU, it's loaded using a 4-bit normal float quantization via bits and bytes, which cuts memory usage dramatically without quality loss. It was pre-trained on heavily filtered web data and synthetic textbook data. No fine-tuning because the model is steered entirely through prompt engineering. Now let me walk you through how all three models work together in the end-to-end pipeline. Step 1 is data extraction and TensorFlow. When you upload audio, the waveform is converted into a log-mil spectrogram tensor and passed to Whisper, which outputs plain text plus exact timestamps. This acoustic metadata is preserved throughout the entire pipeline. Step 2 is vector space difficulty scoring. After Phi3 generates flashcards, each question and answer pair is individually encoded into vectors by SBERT. We calculate the cosine similarity between them. The more semantically distant the question and answer are, the harder the card is. All cards are automatically labeled hard, medium, or easy and wired into a SuperMemo2 spaced repetition scheduler. Step 3 is the cross-model RAG chat. Instead of dumping the entire transcript into the LLM context window, we use retrieval augmented generation. When a user asks a question, SBERT encodes it into a vector and runs a cosine similarity search against the lecture embedding matrix. The top three most relevant sentences are retrieved and passed to Phi3. Because we preserve Whisper's timestamps, the AI cites the exact moment in the lecture in its answer. Step 4 is the Feynman evaluator, which is essentially reverse RAG. Instead of feeding vectors to the LLM, we use vectors to evaluate the student. The student types their own explanation of a concept, and SBERT encodes it and computes cosine distance against the lecture matrix. Based on that score, Phi3 either praises the student or corrects their specific misunderstanding. The app has 4 tabs, all powered by the neural pipeline just described. Flashcards with flip animation and difficulty badges, MCQs with reveal on-demand answers, the Feynman test for evaluating your own understanding, and the RAG chat tutor with timestamp citations. I'll be showing all of these in the demo shortly. The application is deployed on Google Colab using a T4 GPU with 16 gigabytes of VRAM. The UI is built with Gradio, which generates a public shareable URL. For local deployment, anyone with a GPU over 10 gigabytes can clone the repo and run it directly. The 4 core papers are listed as shown on the screen. The Super Memo 2 algorithm citation is also included. The full source code is on the FlashForward GitHub. Here's the FlashForward app running live on Colab. On the left, you have your input panel. You can upload either lecture audio or PDF. I created a short lecture recording, which is what I will be using. Let's play. This is a test. Neural networks are a type of machine learning model inspired by the human brain. They consist of layers of neurons that process input data and learn patterns through training. Deep learning refers to neural networks with many layers. So you can trim the audio, adjust the speed and volume as you like. I will upload this and hit generate. This triggers the full pipeline, so Whisper transcribes it, Phi3 generates the study bundle, and Sentence-BERT pre-computes all the embeddings. In the flashcards tab, each card has been automatically scored by SBERT. This one is labeled easy because the cosine distance between the question and its answer vectors is low. They are semantically close together. I will flip it to reveal the answer, and below you can see the spaced repetition buttons. When I click easy, it triggers our Super Memo 2 algorithm, which mathematically learns that you understand this concept well, so it waits much longer before testing you on it again. The MCQ tab has multiple choice questions generated by Phi3. Let's reveal the answer to this one. So this is my favorite feature, the Feynman evaluator. I'll type my own explanation of a concept from the lecture. Hit evaluate, and SBERT is now scoring my explanation against the lecture vectors. You can see the semantic match percentage and Phi3's personalized feedback here. Now, if I type something completely absurd, it will give a very low semantic score because it has no mathematical proximity to the actual lecture concept. And Phi3 correctly flags it as a misunderstanding. Finally, the RAG chat feature. I'll ask a question about the lecture content. And notice the response cites the exact timestamp from the original audio. This is Whisper's acoustic metadata flowing all the way through to the chat output. This is the full GitHub repository, readme with the setup instructions and the video of the application running. As well as all the details required by the project. This is FlashForward. Thank you for watching.